Welcome to this professional course in Industrial 4.0. This module on ecosystem for smart farming will cover the introduction to agriculture and aquaculture 4.0. Let me introduce myself. I'm Associate Professor Dr. Margaret Chan Kit Yok from the Faculty of Plantation and Agrotechnology, University Technology Mara, Malaysia. The aim of this course is to provide an introduction to agriculture and aquaculture 4.0, its major components, processes and technologies, and how new products and services will impact business and society. 3 objectives, and they are: number 1, provides an overview of precision farming concepts and the tools of precision farming that include GPS, GIS, and VRT. Secondly, it introduces the use of each of these tools within the processes of a precision farming system. And thirdly, discuss economic and environmental benefits. At the end of this course, the learner should be able to understand the various stages of industrial revolutions, understand the future of agriculture and aquaculture and the skill set needed, recognize the drivers, enablers, and compelling forces for agriculture and aquaculture 4.0's advancement, identify the role and importance of data and cloud computing in agriculture and aquaculture 4.0, and finally, describe how organizations and knowledge benefit workers who can better prepare for agriculture and aquaculture 4.0. At the end of this course, the learner should be able to understand the various stages of industrial revolutions, understand the future of agriculture and aquaculture and the skill set needed, recognize the drivers, enablers, and compelling forces for agriculture and aquaculture 4.0's advancement, identify the role and importance of data and cloud computing in agriculture and aquaculture 4.0, and finally, describe how organizations and knowledge benefit workers who can better prepare for agriculture and aquaculture 4.0. In Lesson 2, we will cover the tools of precision agriculture. The keywords in the topic for precision of agriculture are remote sensing, global positioning system GPS, and geographic information system GIS. There are 3 units being covered in Lesson 2: remote sensing, global positioning system GPS, and geographic information system GIS. The details of the subtopics will be embedded in the contents of each unit as we move on. The first unit is on remote sensing. In remote sensing, sensors are responsible for measuring and monitoring all factors in a smart system. The data sensors can simply be handheld devices mounted on aircraft or satellite base. Reference to remote sensors. Remote sensing is one of the most common ways to extract relevant information about the Earth and environment. And the remotely sensed data provide a tool for evaluating crop health, like plant stress related to moisture, nutrients, compaction, growth diseases, and other plant health concerns are often easily detected in overhead images. So what are the remote sensing basics? Remote sensing is a collection of data from a distance on the land and ocean processes. Remote sensing can be defined as the acquisition of information about an object or phenomenon without making physical contact with the object, and thus in contrast to on-site observation, especially the Earth, including on the surface and in the atmosphere and oceans, is based on propagated signals, example, electromagnetic radiation. The term remote sensing was first utilized in the early 1960s to describe any means of observing the Earth from afar, particularly as applied to aerial photography, the main sensor used at that time. Today, because of rapid technological advances, the planet's surface is routinely surveyed in different platforms: low altitude, unmanned aerial vehicles, UAVs, airplanes, and satellites. The surveillance of Earth's terrestrial landscapes, oceans, and ice sheets constitutes the main goal of remote sensing techniques. Remote sensing can be acquired through both active and passive sensors to provide a variety of information about the land and ocean processes. Examples of active sensors is the synthetic aperture radar or LIDAR, and passive sensors are optical and thermal range, multispectral, and hyperspectral. The application of smart sensors in agriculture is illustrated by Kumar et al. 2021 that shows the flow of processes using data collected to make decisions on agriculture management. So you can see remote sensing can reveal in-season variability that affects crop yield and can be timely enough to make management decisions that improve profitability for the current crop. Remotely sensed images can help determine the location and extent of crop stress. Analysis of such images used in tandem with scouting can help determine the cause of certain components of crop stress. The images can then be used to develop and implement a spot treatment plan that optimizes the use of agriculture chemicals. In a broader context, remote sensing activities include a wide range of aspects, from the physical basis to obtain information from a distance to the operation of platforms carrying out the sensor system, and further to the data acquisition, storage, and interpretation. Then, the remotely collected data are converted to relevant information, which is provided to a vast variety of potential end users. Similarly, in aquaculture remote sensing, the data are collected in real time in water, such as the water parameters, including temperatures, dissolved oxygen or DO levels, pH levels, salinity, turbidity, and pollutant concentration. Underwater remote sensor connected to the internet can also monitor heart rate and metabolism, hunger status of cultured fish in cages, ponds, and rivers, thus can conduct feeding accordingly and reduce production costs. Furthermore, chemical contaminants, harmful algae blooms, pathogens, and toxins can be detected and monitored. The future perspective related to real-time sensors inserted in live fish or put in water to measure the stress level of individual fish and to detect pathogens in water is possible. So we move on to the next subtopic on Global Positioning System or GPS. What is Global Positioning System or GPS? GPS is a precise worldwide space radio navigation system consisting of a constellation of satellites, broadcasting, navigation signals, and a network of ground stations and satellite control stations used for monitoring and control. It determines the accurate position or location of an object on Earth's surface, provided in real time when continuous position information is provided while in motion. As a tool for precision farming in agriculture and aquaculture, precise location information can be obtained at any time, allowing crops, soils, livestock, and water measurements to be mapped. Receivers either carried to the field or mounted on implements, allowing users to return to specific locations to sample or treat those areas. The next question is, how does GPS locate locations? The system is based on a constellation of orbiting radio navigation satellites, that is the space segment, an Earth control segment, and the receiver, who is the user segment. They provide continuous position data provided the receivers have a line of sight access to the satellites. The receiver synchronizes its code with the satellites by adjusting the timing of its code generation until the intersection of all the satellites ranging space converge at a single point. Different GPS uses a stationary monitor receiver to calculate the difference between the true position and the determination of a position from the satellites for a point in time. This allows the position of a roving receiver to have a three-dimensional accuracy of 20 centimeters or better. So in the agriculture where GPS systems are available for use, the source of the data collected from GPS become an integral part of the agriculture ecosystem as a tool for precision farming. The development has opened new doors of opportunities for spatial data collection. Farmers use GPS for accurate mapping of field boundaries, roads, and irrigation systems, for precision planting, and for targeting the application of fertilizer and chemicals that combat weeds and crop diseases. GPS also allows farmers to work despite low visibility field conditions such as rain, dust, fog, and darkness. The increased aquaculture productivity by properly harnessing the potentials of GPS to agriculture become useful as in the land and water mapping, flood and pollution management, management of inland captured fisheries, species ecology and conservation studies. In species studies, it allows to track invasive species, endangered species, fish migrations and population changes, patterns of migration, spawning locations, and preferred habitat. It also provides an invaluable utility tool in water quality monitoring. In the study of fish ecology, it enables the development of models of fish abundance, growth, and prey availability with the physical characteristics of the habitat. Similarly, the same procedure can be applicable to disease and pest mapping. There are multiple factors affecting GPS accuracy. What is GPS accuracy? It indicates the degree of how close the GPS measurement to the actual position. Three main factors most prominent are the position of satellites, the features of GPS receivers, and the signal effect from surrounding environment. In the position of satellites, as we know that satellites are the basic elements of positioning. At least 3 satellites are needed to position an object and 1 more satellite to eliminate the errors. The more satellites used to calculate the position, the better level of GPS accuracy it will be. The distribution of satellites is important as well. For example, if the signals come from rather evenly distributed satellites, the GPS accuracy will be higher. The value of precision, or DOP, can be used to calculate GPS accuracy, and a smaller DOP indicates a more accurate GPS signal. The features of the GPS receivers is another factor. The positioning capability of a GPS receiver is one important factor of GPS accuracy determination. The number of Global Navigation Satellite System, or GNSS, and in which frequency bands a GPS receiver can support directly affect the performance of the receiver. It is easy to understand that the more GNSS system and frequency bands a GPS receiver can support, the better the receiver can perform. Moreover, the antenna performance, the position algorithm, and the number of satellite tracking channels are essential factors as well. A great antenna can perform high sensitivity. GPS receivers in the market all have enough tracking channels to trace multiple satellites and ensure a certain GPS accuracy. And finally, it relates to the signal effect from surrounding environment. Since the signals from satellites to GPS receivers need to travel a long way, the propagation environment affects the signal strength and positioning correctness a lot. The ionosphere, the troposphere, signal blockage, and reflection are all elements that cause errors to occur. The ionosphere, which locates between the thermosphere and the exosphere, will slow down the velocity of GPS signals, while the troposphere, which is the lowest layer of Earth's atmosphere, can sometimes cause radio reflections. So next, we look at the Geographic Information System, or GIS. So what is Geographic Information System, or GIS? The GIS is a tool that creates visual representations of data and performs spatial analysis in order to make informed decisions. It is a technology that combines hardware, software, and data. GIS data can be separated into two categories. Spatial reference data, which is represented by the vector. The raster forms, including imaginary attribute tables, which is represented in tabular format. So the next question is, what is the difference between GPS and GIS? Citing Taylor and Engel from Purdue University, US, the GPS is a satellite system that projects information to GPS receivers on the ground, enabling users to determine the latitude and longitude coordinates. While GIS is a software program that enables users to store and manipulate large amounts of data from GPS and other sources. So simply, the difference is that GPS are used to find the exact locations of things, while GIS are used to record information onto the maps. The use of GIS in agriculture makes the work time effective for analyzing and extracted information. It has the capability to analyze soil data and determine which crops should be planted, where and how to maintain soil nutrition so that the plants are best benefited. GIS helps farmers to achieve increased production and reduce costs by enabling better management of land resources. GIS can enhance the decision-making process by allowing the aquaculturist to make informed decisions about the placement of a site. GIS offers an economical and efficient way to analyze and manipulate the parameters involved in choosing a site for aquaculture. The fishery planning and management have many spatial components and severe issues. Spatial components are movements and migration of resources, definition of fishing grounds, transportation networks, markets and habitat loss, and environmental degradation can be grouped into spatial issues. The essential usefulness of GIS lies in its ability to manipulate and overlay data in several ways and to perform many analytical functions so that it can contribute to a faster and more efficient decision-making process in fisheries. In fact, FAO has recently released a web-based portal called GIS Fish, which can be obtained. The global experience on GIS, remote sensing and mapping as applied to aquaculture and inland fisheries. Once again, congratulations, as we have come to the end of Lesson 2. I will leave you to spend some time for reflection with 10 multiple choice questions in the quiz. Thank you.